Problem 1 from 2006 is more electric field and electric potential analysis. However, this word derive comes up in 2 spots, and we got to talk about that because it's something I figured out when I acted as an AP reader the first time. Okay, we've got a negative charge, positive charge right here. On the diagram, indicate with an arrow the direction of the net electric field at point P. These 2 electric fields from top left and bottom right are going to cancel each other out because they're in opposite directions. This top right is pointing up and right, and also, because this guy's positive, it's also pointing up and right, so it looks like that electric field is going to point up and right. Derive an expression for each of the following in terms of the given quantities and fundamentals. That word derive is critical. When they ask you to derive, that means you have to start with a fundamental equation, something from your equation sheet. If you immediately start plugging numbers in on a derive problem, they're probably not going to give you any points. This is something that absolutely killed people on the AP problem that I checked last year. I fundamentally disagree with it, but the university professors are really big on that word derive. So since we're trying to derive the electric field, we have to write down the fundamental electric field equation from the equation sheet, KQ over R squared. If I immediately just started plugging numbers in, I would get the whole problem wrong. So please be careful when they say derive. Notice I'm figuring out the distance between the charge and the point P. That's going to be A over 2 squared plus A over 2 squared. And then we're taking that to the 1/2 power. We get A over the square root of 2. Okay? Since these 2 electric fields are in the same direction, same distance apart, we're going to add them up. So that's 2 times KQ over A squared times 2, because this square root of 2 comes up top, and we get 4KQ over A squared. We now need to derive the electric potential, and once again, I need to start out with a fundamental equation, in this case, KQ over R. We're using the principle of superposition, so I'm calculating the electric potential from all 4 of the particles. Negative, 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 this guy's positive, so that means that I'm going to have 2 times the negative term. KQ over R, R is still A over square root 2 comes up top, okay? Remember, you're calculating the electric potential, so you need to add them up. The pluses and minuses actually matter, so you need to be careful on that. A positive charge is placed at point P, it is then moved to point R, so it's going to move down here, which is the midpoint of the bottom of the square. As the charge is moved, is the work done by the electric field positive, negative, or 0? So what does that positive charge want to do? Well, there's more negative charge up here than down here. The electric field's pointing up and right, so we would imagine that that positive charge needs to move up and right. We're moving the positive charge down, so that positive charge is doing the opposite of what it wants to do, so the work done by the field is negative, okay? Describe one way to replace a single charge in this configuration that would make the electric field at the center of the square 0. Okay, very easy. If I just make this positive up here, then these 2 positives will cancel out. We already know that the 2 negatives cancel out. Okay, I did that wrong. There, 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 there. Everything would cancel out and we would get an electric field at 0. Next one, describe one way to replace a single charge in this configuration such that the electric potential at the center of the square is 0, but the electric field is not 0, okay? A little bit of thought process here. In order to have the electric potential be equal to 0, that means I need to have 2 positives and 2 negatives, okay? So one of the negatives has to change. If I change this to a positive up here, then the electric potential would be 0. The electric field would still be pointing to the right overall, because this guy's pointing down and right if this is now positive. This guy's pointing up and right, so overall to the right. This guy's pointing up and right, this guy's pointing down and right, and we have an overall electric field to the right. So one way to establish this is to change the negative charge into a positive charge. No real calculation on this problem, but please keep in mind whenever they ask you to derive. Derive is something that can completely mess you up on the AP exam. You need to start with a fundamental equation from the equation sheet if they ask you to derive. Watch out for that word.